Hello, let us look at another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication system. So, in the previous module we have seen an introduction to a multi-carrier modulated system. So, now let us look at the transmission scheme, that is the basic principle of operation, the transmission and reception in a multi-carrier modulated system. So, what we are going to see is basically MCM system, and we are going to see the transmission. That is what I want to see is I want to see what is the transmission, the scheme for transmission in MCM, that is a multi-carrier modulated system. As we already said, in a multi-carrier modulated system I have a large bandwidth, that is I have a large bandwidth which is B, and I am dividing it into sub bands, each of band B by N. So, the spacing between these sub bands or the sub carriers is B by N. At each sub band I am placing a sub carrier. So, I have the first sub carrier at 0, second sub carrier at B by N, third another sub carrier at 2B by N, another sub carrier at minus B by N, another sub carrier at minus 2B by N, so on and so forth. So, what I have is I have a sub carrier at each. So, we have multiple sub carriers with subcarrier spacing. Remember, with the spacing between the subcarriers equals B by N. So, I have subcarriers, for instance, at, if I call F naught as the fundamental frequency equals B by N, let us denote by F naught equals B by N, F naught equals B by N. Therefore, I have subcarriers at 0, at F naught, to F naught, so on, as well as minus F naught, minus 2 F naught, and so on. So, basically I have a total of n subcarriers. I have a total of n subcarrier. So, what we are saying is we have divided the bandwidth B into n subbands. The bandwidth of each subband is B by N, and what I am doing in each subband I am placing a subcarrier, right. So, we have subcarrier at 0, B by N, 2 B by N. On the negative side we have subcarriers at minus B by N, minus 2 B by N. So, if we denote this B by N by a quantity F naught, where F naught can be thought of as a fundamental frequency of this system, then I have subcarriers at 0, F naught, 2 F naught, 3 F naught, so on, and on the negative side at minus F naught, minus 2 F naught, minus 3 F naught, and so on. So, I have a total of n such subcarriers. So, the kth subcarrier, so we are denoting the kth subcarrier. So, the kth subcarrier is centered at k times F naught, that is equal to k times B over N. So, this is k subcarrier which is at k times F naught, which is k times B over N, and this subcarrier is given as e to the power of j 2 pi k times F naught. So, we have the kth subcarrier in the system which is given by e to the power of j 2 pi k F naught, okay. And let the kth symbol be given by x of k, x of k denote the kth symbol, then the transmitted signal is x of k, which is equal to, the transmitted signal is sk of t, which is equal to x of k e to the power of j 2 pi k f naught times t. So, this is what is this? This is the signal transmitted on the kth subcarrier. So, the signal transmitted on the kth subcarrier is x k e to the power of times e to the power of j 2 pi k f naught t, that is the symbol x k multiplied by the carrier e to the power of, or the subcarrier e to the power of j 2 pi k f naught times t. This is the signal that is transmitted on the kth subcarrier frequency. Now, you have to sum across all the n subcarrier frequencies. So, the net transmitted signal, or the net transmitted MCM signal, multi-carrier modulated signal, the net transmitted MCM or multi-carrier modulated signal is basically, this is basically given by the sum over all subcarrier, the signals over all subcarrier frequencies, that is x k e to the power of j 2 pi k f naught times t, that is the sum of the transmitted signals across all transmit signals across all n, sum of transmit signals across all the n subcarriers. So, this is summation over k x k, which is the kth symbol, times e raised to j 2 pi k f naught t, which is the kth subcarrier. And now, let us say that the received signal, so this is the transmitted signal. So, let us say I have the received signal, which is given as x k e to the power of j 2 pi k f naught t. So, obviously, here I am ignoring the noise at the receiver. What I am saying is, I am taking the signal across each subcarrier, I am adding up these transmit signals across the different n subcarriers, and therefore, I have some summation x k e raised to j k to e raised to j 2 pi k f naught t, right. That is the sum signal or the composite signal which I am transmitting over the channel, and I am receiving the corresponding signal y t. In the absence of noise, I am saying that the received signal is equal to the transmit signal. I am ignoring the presence of the noise component for the moment. And now, we are going to look at how to reconstruct, that is how to recover these different symbols, because our aim or ultimate interest is in recovering these different symbols x k that have been transmitted on the various subcarriers. Now, how to recover these different symbols? Now, if you look at this expression, for the multicarrier transmitted signal, you will see this is similar to the Fourier series. Notice that this is similar to a Fourier series expansion. So, therefore, x k is the kth Fourier series coefficient, and therefore, the way to extract the Ealth symbol, to extract XL, which is basically symbol on Ealth subcarrier, we have f naught integral 0 to f naught e to the power of minus j 2 pi L f naught times t times y of t. This is the operation, because remember what is XL? XL is the Ealth Fourier coefficient of the signal y of t, and therefore, my process to extract the Ealth Fourier coefficient is simply f naught integral between the limit 0 to 1 over f naught, that is the fundamental period of the signal. 1 over f naught is the fundamental time period of the signal, integral 0 to 1 over f naught y t times e to the power of minus j 2 pi L f naught t dt. That will give me the Ealth Fourier coefficient, and this can be seen as follows. Now, if you look at this, this is f naught 0 to 1 over f naught. I am going to substitute the expression for y t. So, this is integral e to the power of minus j 2 pi L f naught t times y t, which is summation over k x k e to the power of j 2 pi k f naught t. Now, therefore, if I take the summation outside, I am going to have summation over k x of k x of k times f naught integral 0 to 1 over f naught e to the power of j 2 pi k minus L f naught t dt. Now, look at this quantity. If I look at this quantity, integral 0 to 1 over f naught e to the power of j 2 pi k minus L f naught t dt. This is a sinusoid with fundamental period f naught, and the integral over 1 over f naught, this is equal to, from a basic knowledge of Fourier series, you know that this is equal to, well, if k is equal to L, this is equal to 1, if k is equal to L, this is equal to 0, if k is not equal to L. So, what are you doing? You are taking a sinusoid with a fundamental period 1 over f naught, and you are integrating it over 1 over f naught, that is, you are integrating it over a period. Therefore, this is going to be non-zero if it is a sinusoid, that is, if k is not equal to L, it is a sinusoid at a multiple of the fundamental frequency f naught, its integral over the fundamental period 1 over f naught is 0, and the only scenario in which the integral is non-zero if k is equal to L, which means the sinusoid reduces to a DC signal, and for a DC signal the integral over a fundamental period is simply equal to 1. And therefore, now if you look at this integral that we have over here, that is, if you look at this integral, that is, I have summation, that is, from the previous page I have summation k over k x k f naught integral 1 over f naught e to the power of j 2 pi k minus L f naught t dt. In this, only the term corresponding to L, that is, term corresponding to k equal to L, will survive. So, therefore, I will have this as summation x k delta k minus L, where delta k minus L is equal to 1 if k equal to L, is equal to 0 if k is not equal to L. Therefore, in this summation only the term corresponding to k equal to L will survive, and therefore, I can recover x of L. So, what are we doing? At the receiver we are multiplying by the corresponding Ealth subcarrier e to the power of minus j 2 pi L f naught t, integrating over the fundamental period 1 over f naught to recover the symbol XL transmitted on the Ealth subcarrier. This can be done similarly for all the N subcarriers to recover all the N symbols transmitted on the various subcarriers. This is termed as coherent demodulation. So, at the receiver we employ coherent demodulation, we employ coherent demodulation with e to the power of minus j 2 pi L f naught t to extract x of L. Thus, by correlating with e to the power of correlating with e to the power of j 2 pi L f naught t or matched filtering, e to the power of minus j 2 pi L f naught t minus t, the match filter is H conjugate t minus t, one can extract symbol on the Ealth, one can extract the symbol on the Ealth subcarrier. This is the principle and this is the transmission and reception scheme. So, this is the principle of MCM. This is the principle of a multi-carrier modulated system. So, basically to summarize what we have is, earlier if you remember we had a single carrier system. In a single carrier system I have a bandwidth of B and I have a symbol time t equals 1 by B. So, I have a symbol time t equals 1 by B and therefore, in n by B I am transmitting, therefore, I am transmitting n symbols in symbol time n by B equals the total time, and this is for a single carrier system. However, in our multiple carrier system what we are doing is each symbol on each subcarrier. For instance, if I look at each symbol on each subcarrier, this has a time of. So, if in a multi-carrier system, if I look at this, each symbol on each subcarrier has a time of n by B. However, I have n subcarriers, therefore, I am transmitting n symbols in, I am transmitting n symbols across these n subcarriers in this multi-carrier system. So, what I have, if you look at this net, I am transmitting n symbols across n sub carriers, all right, and the total symbol time remains fixed. The total symbol time is n by. So, here we have a comparison between a single carrier, and this is my MCM system or multi-carrier. So, the comparison, this is a pictorial comparison between a single carrier and a multi-carrier system. In a single carrier system, we have a bandwidth of B, the symbol time is 1 over B, therefore, each symbol is 1 over B. So, we have symbol at 1 over B, 1 over B. So, in time n over B, we are transmitting n symbols, correct. However, in a multi-carrier modulated system, we have n sub-carriers, the symbol time is n over B. So, we are increasing the symbol time, that is symbol time has been increased to n times that of a single carrier system, symbol time is n over B, but we are transmitting n symbols in parallel across the n sub-carriers. So, each symbol has a time n over B, that is the difference between single carrier and multi-carrier modulated system. So, a multi-carrier modulated system can be thought of as a parallel transmission, as having several parallel channels between the transmitter and receiver, each of bandwidth B divided by n and each with symbol time n divided by B, and n such channels or n such sub channels or n such sub bands are used with n sub carriers to convey n symbols in parallel between the transmitter and receiver. This is in short, this summarizes the philosophy and principle of multi-carrier modulation. As we already seen, this helps avoid inter-symbol interference, because the symbol time in each sub-channel is much larger than the delay spread, and also what we have seen is we have seen how to modulate the symbols on the sub-carriers, how to demodulate using coherent demodulation based on our principle of the Fourier series, or right. So, this is a very intuitive way to modulate and demodulate in this multi-carrier modulated system, and this is a precursor, or this forms a basis for the OFDM system, which we are going to start exploring in the subsequent modules. Thank you very much.